In this presentation, I'll be explaining different controls of wind turbine controls. Now let us see the wind turbine concept. There are two forces. One we call it as lift force. Another one is called drag force, or lift based and drag based. Coming to the lift based wind turbine, in that one, if you see the airfoil is this one. Airfoil here, the wind direction is this one, and here the distance to be traveled by the wind in the upper side of this airfoil is more compared to lower side. Since the distance is more here, velocity is more in the upper side compared to the lower side. Or as per Bernoulli's principle here, we can say that pressure will be higher at the lower side and than the upper side. So there will be a pressure difference, that is the differential pressure caused by the flow over the airfoil shaped body leads to a net lift force. That is, a net lift force comes here because of the pressure difference on the upper, and here more pressure compared to here. A lift force comes in the perpendicular to the wind direction, and as the wind direction, this lift force, you can say that one they say the horizontal axis, wind turbine here, this is a lift force that causes the blade to rotate. So that is the lift force is the one. Second one is the drag force based wind turbine. In that one, Savonius rotor, in that force is using, drag force is using. In that, here as an example here, there are two. As wind is the wind waiting on the concave and convex sides of this one, and because of the difference in forces, a torque will be produced, and that will be rotating that one. Therefore, here this is that is Savonius rotor, that is a drag force based wind turbine. Therefore, this is a drag, that is actually that drag force is along with the wind flow. Therefore, there are two forces. One we call it as lift force, that is perpendicular to the wind direction, and drag force, this is in the same direction as the wind. Therefore, these are two forces acting on the wind turbine. Continuing the flow of wind over the aerofoil here, this aerofoil here can say that one upper distance is more than lower distance, for the velocity here more than this one, and the wind stream at the top of the aerofoil has to traverse a longer path than at the bottom, leading to a difference in velocity. The velocity will be difference in the, and this give rise to a difference in pressure. That's called Bernoulli's principle. There will be difference in pressure, or here the pressure will be more, lower side pressure will be more than upper side, and due to this difference in pressure, there will be a force acting upward perpendicular to the wind direction. That force we call it as lift force. And there's another force that tries to push the aerofoil in the direction of the wind, and this is called drag force. The drag force is the same direction as the wind direction. The net force on the aerofoil is then determined by the resultant of these two forces that decides the net force acting on the aerofoil. Therefore, the lift force is perpendicular to the wind direction, and drag force is in the same direction as the wind direction. Let us see some nomenclature of aerofoil and some basic definitions. This aerofoil basic definition. One is the leading edge. This is the leading edge. Leading edge, this is the point at the front of the aerofoil that has maximum curvature. This is called the leading edge. And trailing edge, that is defined similarly as the point of maximum curvature at the rear of the aerofoil. This is the trailing edge. And the chord line is a line connecting the leading edge and trailing edge. Therefore, chord line, this is a straight line connecting the leading edge and trailing edge of the aerofoil. And this is the wind that's coming, this angle of attack. And here, these are the different, this is a chord line, this is a leading edge, this is the trailing edge, and this is the upper surface, and this is the lower surface. And therefore, these are the nomenclature, different basic definition of a aerofoil. We'll see the more definition in the next slide. Continuing the basic definition of aerofoil, that is chord length. Chord length is the length of the chord and is the characteristic dimension of the aerofoil section. That is the length of chord. That is called chord length. And pitch angle, the angle between the chord of the airfoil section and the plane of rotation, also called as setting angle, or that's called the pitch angle. That's actually an angle of attack actually. Angle of inclination is the angle between the relative velocity of the vector and the plane of rotation. That's called angle of inclination. And solidity is the ratio of the blade area to the sept area. For certain definitions of this aerofoil, basic definition. Another definition of lift force as well as drag force. Lift force, it is the component of the aerodynamic force in the direction of the perpendicular to the direction perpendicular to the relative wind. Relative wind is that this force, as I already explained, this is called the lift force. That because of the difference in pressure, a force perpendicular to the wind comes. That is called the lift force. And drag force, it is a component of aerodynamic force in the direction of the relative wind. So this is a drag force, and the resultant force will be perpendicular. I mean, the sum of these two, vectorial sum of these forces. That is the resultant force that is acting on the aerofoil. Continuing the basic definitions of aerofoil, that is tip speed ratio, TSR. It is the ratio of the speed of the outer blade divided to the undisturbed natural speed of the wind. For another representation as an equation, TSR lambda equal to tip speed of the blade divided by the wind speed. That ratio lambda, which is called tip speed ratio, tip speed ratio, TSR. Lambda equal to omega by V, omega r divided by V, where r is the radius of the rotor and V is the speed of the wind in meters, and tip speed ratio is equal to lambda equal to tip speed of the blade divided by the wind speed. So that is another one is startup speed, wind speed at which the wind turbine blade will begin to rotate. That is called startup speed. And cut-in speed is the wind speed required for a particular wind turbine to begin to generate the electric power. That is called minimum, that much speed is required. That's called cut-in speed. And cut-out speed is called, this is the speed at which the turbine blades are brought to rest to avoid damage from the high winds. Therefore, the cut-out speed is the maximum permitted value of the speed, and cut-in speed is the minimum speed for which to generate the electric power. Cut-in speed, cut-out speed, startup speed, and tip speed ratio, TSR. Therefore, these are certain definitions related to the aerofoil. Already we have seen the lift-based wind turbine concept. As already we have seen because of the difference in pressure at the lower and upper side of the aerofoil, upper side pressure will be less than lower side, therefore force will be acting. That force is called the lift force, and this is called drag force. And the resultant of that one is the resultant force that is acting on the one. This is again this is a windmill in which the lift force that rotates the blades is coupled to the generator. So that is this is actually horizontal windmills, or this is a horizontal axis wind turbine system in which the lift force will be rotating the blade. The rotor efficiency varies as the tip speed ratio changes. A function of speed ratio, that is, there's a plot like that one, and that shows that the rotor efficiency versus tip ratio for the rotor with a different number of blades, and that's number of blades, or that is two blade rotors have the highest efficiency. From this plot, it is clear that the two blade system is having the highest efficiency, and this shows a graphical representation of the variation of the efficiency or rotor efficiency with respect to the tip speed ratio for different conditions, two blade cases and Darius rotor and modern three blade rotor, like the different conditions or different setups. What is the rotor efficiency? It shows that for a two blade rotors have the highest efficiency, that is this one. High-speed propeller type wind machines, that horizontal axis wind turbines that are used today for the electrical generation, do not operate on a thrust force, as mechanical force generated by the engine. They operate mainly on the aerodynamic force that develops when the wind flows around the blade of aerofoils. Aerofoil, as already we have seen that working of aerofoil already I explained. is a structure with a curved surface designed to give most favorable ratio of lift to the drag in flight and used for the basic form of wings. So this is actually in aeroplane also same principle as that lift force, drag force in the what both are acting on this aerofoil. That is. Now let us see the power control of wind turbine. The basic purpose of the wind turbine is to harness maximum wind energy so that the electrical output power is maximum. During stronger wind, it may be required to waste some of the excess energy in the wind in order to avoid damage to the wind turbine. In the view of that, some type of power control is provided in the wind turbine. Otherwise, if the wind is very strong, that may cause to the damage of the wind turbine. Therefore, that should be avoided. Therefore, the aerodynamic force acting on the turbine rotors are controlled so that power in very high winds can be controlled without damaging the wind turbine. Therefore, the power control of the wind turbine is required. Now, different wind turbine control systems. Let us see that horizontal axis wind turbines have to be oriented to face the wind. In high winds, it is desirable to reduce the train loads and protect the generator and the power electronic equipments from the overloading. At low and moderate wind speed, the aim should be to capture high power as effectively as possible. Therefore, wind turbines can, based on that, wind turbine can have a different types of control mechanism. One we call it as pitch control, pitch angle control, then stall control and yoke control in order to implement this one, or in order to exact overloading, to avoid the overloading when a high wind is coming. Similarly to if it is a low, to extract the maximum power from the effectively from the available wind. Therefore, in order to do this one, there are three types of control like pitch angle control, stall control and yoke control. First one comes to the pitch angle control or pitch control. Pitch angle control, pitch control to maintain the optimum blade angle to achieve certain rotor speed or power output, certain power output. To optimum the angle of blade angle is suggested. So this system changes the pitch angle of the blade according to the variation of the wind speed. Pitch angle is changing as per the wind speed. And here there is a active pitch control mechanism is there, and with the pitch control it is possible to achieve high efficiency by continuously aligning the blades in the direction of the relative wind. On the pitch control machines, that is pitch control that adjusts the blade angle, the pitch control machine, as the wind speed exceeds the rated speed, the blades are gradually turned about the longitudinal axis and out the wind to increase the pitch angle. This reduces the aerodynamic efficiency of the rotor and the rotor output power decreases, because in the case when the as the wind speed exceeds the rated speed, this is done by this pitch angle control. Therefore, that is the pitch angle control or pitch control. Here the active pitch control, and then there is a blades pitch. Symmetrically it controls that one. That angle of this blade is controlled by this pitch angle control system. In the pitch angle control, pitch control, in this type of control, when power output becomes too high or too low, rotor blades can be turned out or in to the winds respectively. Can be turned out or it can be turned in as the wind speed is either very large or very low. So that when the rotor blades are turned out the wind, there will be a gradual reduction in lift or the blade. Lift force will be reducing. To reduce the power significantly, this type of control requires a large change in pitch angle blade. Now in turbine with this type of control, turbine blades is adjusted to shed some of the wind when the output power exceeds the specification. Good power control can be achieved with this type of control. Therefore, if the wind power is or wind when the rotor blades are turned out the wind, that is if output becomes too high, that is if the power output becomes too high in this type of control, then rotor blades is to be turned out. That can be done by using the pitch control. That is, this is the tower. This is the, of course, blades, and this is, the pitching direction, so that blade angle will be changed. Pitch control mechanism is shown here. When the wind speed exceeds the safe limit for the system, the pitch angle is so changed that the power output reduces to 0 and machine shifts to stall. If it is too much, then pitch angle is changed in such a way that machine shifts to stall mode. That comes to a stall mode. At normal wind speed, the blade pitch angle should be ideally settled to a value which the output power equals to the rated power. That is a normal wind speed. Anyway, by adjusting the pitch angle, we can have the power output can be changed. That is done by the pitch control mechanism, or the angle of the blade related to the wind speed is adjusted. Second control called the stall control. Stall control is generally applied to limit the power output at a high winds to constant pitch turbine, driving the induction generator connected to the network. Therefore, blades are bolted to a fixed angle onto the hub. And in this control, the rotor blades are turned up against the wind, and hence these blades will stall and therefore lifts the turbine blades and lifts on the turbine blades, and that will be reducing automatically. In stall control turbine design, turbine blade is done carefully in order to reduce the efficiency automatically when there will be a stronger wind. And in passive stall control, design of rotor aerodynamics leads to the rotor to stall. That is, this is applicable when the wind speed is more than allowed limit, upper limit. Then this stall control will be active. In active stall control method, stall of the blade is actively controlled by pitching. The blade regulates the power output of the wind turbine by adjusting the rotor blades. For low wind speed, pitching to the blade is similar as in the case of pitch control wind turbine, so that the maximum efficiency can be achieved. The wind speed is less low. And for higher wind speed, the blades are slightly pitched into the direction opposite to that of the pitch control turbine, so that blades can be deeply stalled. And the main advantage of active stall control method is that it can compensate air density variation. Air density variation can compensate by this active stall control. And this is the active stall control. That is, if the wind speed is more than rated speed, that active stall control comes into picture. That is graphically it is shown that one. Third control is the yoke control. Yoke control means the yoke control is a mechanism that helps wind turbines rotor to face the wind, and to extract the maximum power output. And it helps the turbine to capture the most wind possible. Maximum wind possible can extract. That is done by this yoke control. Of course, there's a yoke control system motor is there. And yoke control is important because of the wind directions can be changed quickly. And the misaligned turbines can cause the loss of power. So wind direction will be changing quickly. And in order to cope with that one, will be changing, though the yoke control motor will be acting, and so as to facing the wind in that changed direction. Therefore, the yoke control mechanism comprises that consists of a motor and a drive system. And the main purpose of this arrangement is to move the nozzle and blades according to the wind direction. To move the nozzle and wind direction, this one, and wind, to enable the wind turbine to capture the maximum available wind. Therefore, that is the purpose of using yoke control. That is used in a horizontal axis, wind turbine. In that one, by changing this one, you can extract as the wind speed direction is changing. That is, in that case, the yoke control will be active and to extract the maximum power. Therefore, it is shown here, and this is the of course, your system control as such, that consists of motor that will be changing the the direction of this one, so that it can extract the maximum power from the wind as the wind direction changes. That's the third one, yoke control. That is applicable to the horizontal axis, horizontal axis wind turbine.